All right, in part B, we're going to look more at probability distributions for the binomials and how do you calculate these, especially using our calculators to get past those crazy formulas. All right, so how to calculate these guys using our calculators. All right, you're going to hit second vars, gets you to the distribution menu. You're going to choose either, there's two options, binomial PDF or binomial CDF. Okay, CDF stands for cumulative distribution function. PDF does not stand for cumulative. So there's different times you use each one. So I'll show you those. But either way, when you pick those, it's going to ask you three things. It's going to ask you how many trials, what's the probability of a success, and then how many successes are we looking for, right? All right, so this is what it's going to look like when you hit PDF. And it asks you for those three parameters, and it computes when x is equal to a specific value, a number of trials, like I want 4 successes or 3 successes, okay? And you're like, well, what else would it be? Well, it could be more than that, like we saw in the previous video. So this is, I think of this as P is for perfectly equal to some value. That's when I use PDF. So then CDF, cumulative distribution function. That's when x is less than or equal to a value k. So it's that value and below, everything below it. So if I get 4 successes, this is going to compute for me 0, 1, 2, 3, and 4 successes all at once. It's going to run that equation for you 4 times. And find the sum. So it saves you a lot of time and energy. But you do have to make sure you've clearly distinguished which function you used and the parameters. So for instance, with the roulette example we've used before, if x is 4 successes, I would choose binomial PDF and I would label. You have to label these. If you don't label them, you don't get credit. N is 10 spins. Probability of a success is 18 out of 38. Number of 4 successes gives me a probability of 0.225. All right? But what if it asks me, what's the probability that it's greater than or equal to 8? Well, remember, this is a less than or equal to function. So I have to think about the distribution. If I only want 8, 9, and 10, like I did on the previous video, I have to take away all the successes 7 and below, if that makes sense. All right, so what I'm going to do is actually, remember, one of the rules of probability is they all have to add up to 1, right? So if I take 1 and I subtract the probability of 7 blacks and below, then I get the probability of 8, 9, and 10 added up. So how do I do this? Well, that means I would do binomial CDF with n of 10, probability of success, where x is 7. All right, now, anytime it's a greater than or equal to, here's a pattern for you to catch. It's greater than or equal to 8. I'm going to subtract the cumulative distribution function of 1 less. So this would be 7, okay? And I can go back over that in class if you need me to. Because of the complement rule, this is why this works. All right, but notice it's not right here, it's not an 8, it's a 7, all right? So is it okay to use the binomial PDF and CDF on the exam? Yes, it is. But you have to be careful. You have to show adequate work, otherwise it won't give you credit. What do I mean by that? Well, you have to be clear and label, did you use the binomial PDF or CDF? And you have to label, what does X represent? In this case, how many times out of the 10 did it land on black? Don't just say success. Explain what the success is in context of the question. And you have to clearly define how many trials, what's the probability of a success, and how many successes we're wanting, all right? No labels, no credit, seriously. All right, now, another thing they may ask you to do is to find what's the mean and standard deviation of a binomial distribution. Well, there are formulas for this, all right, and they are in your chart, so you have to memorize them. So mu, mean, is simply n times p. So that's number of trials times the probability of a success. Easy peasy. And then sigma, the standard deviation, looks like this. It's n times p times the complement of p, and then you take the square root of that. All right? So it's pretty simple. If you know n and p, you can find these guys really easily. All right, let's walk through an example. So if x is the number of the next 10 spins of a roulette wheel that land on black, A, calculate and interpret the mean and the standard deviation of x. All right, there's our formulas. So the mean would be where n is 10, and the probability of success is 18 out of 38. Okay, so for mean, I'm just going to multiply these, and I get 4.74. When I interpret this, I would say if we spin 10 times over and over, that's the repetition, we can expect to land on black 4.74 times. All right? Now for standard deviation, plug in my n, probability of success, a complement, do all that calculation in my calculator, I get 1.58. To interpret standard deviation, I would say if we spin 10 times, many times, the number of black spins will typically vary about 1.58 from the mean. So notice the phrase, will typically vary from the mean. It's always part of your interpretation. So B, how often will the number of spins that land on black be within one standard deviation of the mean? All right, this is a little bit complicated, so hang on. One standard deviation of the mean. Well, if the standard deviation is 1.58, and this is the mean, that means it could be 1.58 below this number or 1.58 above. So I have to consider both. So I'm going to subtract standard deviation from my low end and add it for the high end. That's what I'm doing right here. So when I do that number, I get this. Okay? Not going to worry about the fact that it's not exactly 3 or exactly 6. Just leave it as decimals. That's okay. Now, I need to find the probability that x is less than or equal to 6.32 because this probability is going to be higher than this probability. That's why I put it first. Okay? And I know that because it's simply because it's a bigger number. So I need to find this probability, and then I find this probability, and I subtract it, and that will tell me the answer to the question being asked. So I'm going to do the binomial CDF. It's a cumulative distribution function, where x is equal to 6.32 first. Then I'm going to subtract the binomial CDF, where x is equal to 3.16. Calculator's going to do all that for me, and I get an answer of 0.65. So when is it okay to use the binomial distribution when sampling it without replacement? If you don't replace something, that can affect the independence of a situation. Almost all real-world sampling is without replacement, which will violate the independence condition of bins. So it could become an issue if we're going to be black and white about it. But there's something called a 10% condition that gives us a little leeway. The issue is, as long as the population is a lot larger than your sample, not replacing 1 or 2 is not going to make a big deal in the probability. That's what the 10% condition is saying. Well, then the question is, well, what does much larger really mean? So when taking a simple random sample of size n from a population of size capital N, we can use a binomial distribution to model the count of successes in the sample as long as the sample is at most 10% of the population. It's more than 10%, then the independence thing is going to be a problem. So mathematically it looks like this. The sample size has to be less than or equal to 1/10 of the population. And you could write this as a decimal. That's fine too. So sometimes we have to check the 10% condition if we realize that the sampling is done without replacement. And this is going to be an important concept that we use throughout the course. So let's look at this example. A cereal company that put 1 of 5 different cards into each box of cereal. Each card featured a different NASCAR driver. Jeff Gordon, Dale Earnhardt Jr., Tony Stewart, Danica Patrick, or Jimmy Johnson. Suppose that the company printed 20,000 of each card, so there's 100,000 total boxes of cereals with a card inside. If a person bought 6 boxes at random, what's the probability of getting 2 Danica Patrick cards? All right, so first thing I have to do is decide what am I looking for? Well, X is, in this case, the number of Danica Patrick cards that I got out of 6 different cereal boxes. All right, I've defined what X is. Now I need to decide, is X going to be a binomial random variable? So I check bins. Okay, a success is getting a Danica Patrick card. A fail is anything else. Independence. Okay, well, I'm sampling without replacement, so this could be an issue. But let's look at our sample size. It's only 6, which is less than 1/10 of 100,000, which is 10,000. 6 is definitely less than that. So since it's such a small number, it's not going to affect our probability. So this condition is acceptable. It's met. N is how many trials. Well, we picked 6 different boxes. And S is the probability of a success is 20.2. So 20,000 out of 100,000 is 0.2. Now, we can use the binomial equation. So if I have 2 cards out of 6, I have 6, choose 2, probability of success to the second power, probability of failure to the remaining 4 power. All right, crank it out. I could put it in the calculator, and it would look like this in my calculator. Notice I've defined my variable right here, and I've given the calculator information right here and defined n, p, and x. So there's my probability. So I would need to interpret this. So there's about a 24.58 probability of finding 2 Danica Patrick cards out of the 6 cereal boxes randomly chosen.